Hey guys, this is Kerry, and in this video we are going to be doing homework number 4's answer key. So which of the following is the graph of g of x equals x minus 3, all square rooted, minus 5? So to solve this, we got minus 3 as an inside transformation. And as you guys said in class, I think Joe taught you, right, that this means it's going to be for the x variable and in the opposite direction of what you expect. So if it's x-axis is left and right, so this is going to be, you would think left 3 because it's negative, but it's the opposite of what you expect, so right 3. And then here you've got an outside transformation, which would be the y direction, so up, no wait, this one is not the opposite, this one is in the direction you expect, so down 5. So we are going right 3, down 5. So we'd imagine that we started at 0, 0, we go right 3, oh that's not right, shoot, right 3, down 5, that's not correct, right 3, down 5, this one is our answer. On the grids below, draw rough sketches of each of the following functions, make sure to label the vertex with its coordinates, state the domain and range of each of the functions you have sketched. So here you've got an inside transformation of plus 4, that's the opposite of what you expect, so left 4. 1, 2, 3, 4. Then we go for the outside transformation down 5. So 1, 2, 3, 4, 5. So left 4, down 5, and then we draw the square root shape because this is a square root graph from there. Now for our domain and range, the domain is all of the included x values. So you set up the inequality notation, and the range is going to be all of the included y values. So you set up the inequality notation there. So here our domain goes from negative 4 all the way to, there is no end, to infinity here. And our y values will go from negative 5 all the way up, because this keeps going up forever, to infinity. So this is our domain and range. You're going to do part B on your own. Use the above, I guess I didn't give you the table, but you can determine each of the following. So for cube roots, the way you want to do these is you want to break it down. So 64, we break it down over here, that's 8 and 8, 2 and 4, 2 and 4, 2 and 2, 2 and 2. So it looks like we've got 2, 2, 2, 2, 2, 2. And the way cube roots work, right, is instead of like square roots, you're trying to find groups of, so instead of square roots where you're trying to find groups of 2, you're trying to find groups of 3. So we have one group of 3 here, one group of 3 here, so we can write that as the cube root of 2 cubed times 2 cubed, and cube roots and cubes cancel out, giving us a 2, cube roots and cubes cancel out, giving us another 2, so 4 total. Let's do one more of these. Cube root of 27. So if you break 27 down, that gives you 3 and 9, 3 and 3. So this is the cube root of 3 times 3 times 3, which is 3 cubed. Cube roots and cubes cancel out, giving you just 3. Simplify the expression below to simplest radical form. So this one is a square root. So with a square root, we're trying to find things squared. So it looks like we've got x times 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 x. Let's count it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we've got a whole bunch of y's. So the whole idea with these problems is at first it might be hard to find shortcuts, but I think you can find some here. So we want to write these as squares because we have a square root. No number there. So we've got 1, 2, 3, 4, 5 pairs, and that should kind of make sense. 5 pairs gives us 10 total x's. So we've got x squared, x squared, x squared, x squared, x squared. Now to make y to the 11th, we probably have a bunch of pairs. In fact, we probably have 5 full pairs plus 1 extra to make the 11. So we've got y squared, a bunch of those. And I'm just going to mark here that there's 5 of these. So I don't like writing out too much once I start finding these patterns, but I think what we see here is square root and square cancel. Square root and square cancel, and that's going to happen a total of 5 times, so we end up with x to the 5th. Similarly for y, square root and square cancel. Square root and square cancel, and that's going to happen a total of 5 times, but there's still a leftover y inside of the square root. And that gives us x to the 5th, y to the 5th, times the square root of y. So if you need to write out all the y's, that's okay also. You'll find these patterns quick enough. Simplify the expression below to simplest radical form. So with this one, because it's a cube root, we're trying to break it into groups of 3. So we want to end up with a bunch of x cubes. So for the first one, let's do this kind of a long way. So x to the 12th. There's a bunch of x's here. And maybe as you're writing these out, you start to see that there's 1, 2, 3, 4 groups of 3. So you've got a whole bunch of x cubes. Now, in addition to that, you might start thinking, is there a short way to do this? Well, we're going to have a whole bunch of y cubes as well. In fact, to make 30 of them, we'll be able to have 10 groups of 3 to make 30 total. So y to the 3rd, 10 total of these. And then for z to the 301, it looks like we're going to be able to make, let's see, how many groups of 3 do you think we'll be able to make with this one? Z to the 3rd, another z to the 3rd. Well, because 100 times 3 is 300, we'll be able to make 100 full groups, and then 1 extra z to make it 101. So now when we put everything together here, let's see what we get. We get, oops, and this is a cube root, guys. Sorry, I keep forgetting to write that. Cube roots and cubes cancel, so we end up with x to the 4th. Well, how would you go from 12 to 4 quickly? Well, if you divide by 3, it tells you how many groups you make, and that tells you how many x's you end up with. So y to the 30th divided by 3, that gave us 10 groups, so we end up with y to the 10th because all the cubes cancel with the cube root. Z to the 3rd, we end up with 100 full groups, and all of those cubes cancel. And it leaves us with, inside of the cube root, that 1 extra z that had no partners to make a z cubed. Simplify the expression below to simplest radical form. All right, this one is our toughest one yet. Let's see. Ugh, and there's one more after it. I'm going to let you guys do that one, even though it's a 4. Simplify the expression below to simplest radical form. So first step, to take care of the number, you do need to break the number down. It looks like for me that number is going to be 2 and 81, 9 and 9, 3 and 3, 3 and 3, 3, 3, 3, 3, 2. So we end up with the cube root of 3 times 3 times 3 times 3 times 2. Now these ones, a to the 60th, you could write it like that still, but if you think about how many full groups you can make, you're trying to make groups of 3. It looks like you can make 20 full groups, because 20 times 3 would give you a to the 60th. And then to make b to the 14th, you're going to have a bunch of b to the 3rds. Let's see how many. It doesn't perfectly divide it, but it looks like we can make 4 full groups, and that would give us 12, and then we'd have 1 extra b squared left over. So let's see what we get. Because this is a 3 cubed in disguise, cube and cube roots cancel, that gives us a 3. Cubes and cube root cancel, so that gives us a to the 20th, because we had 20 total groups. Cubes and cube roots cancel, that gives us b to the 4th, because we had 4 full groups. And then in terms of the stuff that wasn't a full group, inside of the cube root, we've got 6 b squared. Wow, I drew a very long radical, but didn't really need to. And that's going to be our final answer. So now when you think about 4th roots, think about what group size you're trying to break these into so that you get your 4th roots and 4th powers canceling. Good luck, guys, with problem 7. See you in class tomorrow.